So Tomas, we talk about Trocq and parametricity.
All right, so I'm presenting about Trocq parametricity translations today for inductive types. I don't have much time, so I'm gonna start with the motivation, then bring a bit of the context of the Trocq proof transfer framework, and end up with a few examples of a derivation for this parametricity translation that I'm generating automatically. So let's start with this definition of types. On the left-hand side, you can see a unary representation for natural numbers and a binary representation. And on the right-hand side, you can see the definition for integers. And it might have happened to you that you have proven a more general lemma, a lemma for the more general type, in this case Z, and this appears to you in the form of NAT, for instance, in the commutativity of addition, or that you know how what the result is for folding the addition over a list of natural numbers, and you want it for the folding of the addition in Z, or you just want to have again the good reasoning principle that you have on natural numbers, but on the binary representation. So one would like this to be discharged just by pressing a button, and my colleague Vojta here presented that, you can do this using parametricity, and it has been done previously. On the dependent type setting, it started with the raw parametricity translation, which then was enhanced by the remark that this translation preserves type equivalences in the univalent parametricity translation. And in parallel, there was RocqPL' to change representation between refined data types. So the latest framework to do proof transfer using parametricity is Trocq, and it generalizes over these previous parametricity translations. So on the left-hand side, you have a few examples of what you would like to transfer from one type to the other. So for transferring the 5 natural number into the 5 in Z, user has to provide a relation, the embedding relation from NAT to Z, and Trocq would translate type NAT into type Z. And if you want to translate from list of NAT into list of Z, the user has to provide a proof that this type parametric container list preserve the embedding relation. And if you would like to transfer the contained type in vectors, you will, without translating the indices into another type, you will need to provide a relation from NAT to NAT. So I'm presenting an automatic derivation for generating what the user has to provide for 2 and 3 automatically for a restricted class of inductive types, which is with type parameters, possibly performing recursion, but no indices for the moment. This is done automatically. So now a bit of context. Trocq is able to support weaker relations by using asymmetrical presentation for type equivalence, in which you have this sigma asking for a relation, and you describe how your the maps that go from A to B, and how this, and on the opposite relation you have another map, and this describes a hierarchy, and the closer the the map is to type 4. In this case, I'm going to show what maps looks like. The closer is the relation of being a type equivalence. So we start at the bottom with M0. This is a map that only requests a relation between the two types. Then you have to the user would have to provide a map from A to B. Also providing what's below, and the level above splits into two different ways. So on the left-hand side, you need to provide a proof that the graph of the map is included in the relation, and on the right-hand side, that the relation is included in the graph of the map that you are giving. So above that, you have both of these intermediate conditions on the second level, and at the top you have a coherence proof saying that the left-hand side, when composed to the right-hand side, cancels out. So there's pros and cons from the part of from the side of the user when supporting weaker relations. The pros being that you actually can proof transfer using weaker relations, and this enables avoiding the use of the univalence axiom when possible. And one of the cons is that, they're currently, previous to this work, there was no automatic generation, so the user would have to prove for every level of the lattice that the type parametric container preserves those types of relations. And if you don't want to translate a term, you would have also to provide that your type is related to itself at every possible level in the lattice. So now this is the part where I show how these terms look like, and I'm generating this automatically, but I'm just showing an example here. So the strategy I take is to build bottom-up, to make a bottom-up derivation of this lattice, so as to avoid the use of the univalence axiom when I can afford to do that. And this requires a careful implementation of this intermediate level that's so that when you reach the top of the lattice, you can actually prove that the composition of these two intermediate data can cancel out. And the strategy is by postponing the elimination of identities. So this is, I gave LP a shot. I'm building upon the binary parametricity translation plugin that's available in LP and on top of Derive plugins. And I'm automatically generating this, that the type parametric containers preserve relations across the containers, and that the types relate to themselves at every level. So far, for levels n, 0 for every n that you can have in the lattice. And you can find it on my personal fork of the Trocq repo, and hopefully one day will be merged in the original one. So now an example derivation. This is the parametricity translation for the natural numbers. It relates 0 to 0, and for every related natural numbers, the successor of those numbers are related. The map that you give, it's the one that maps every constructor to the same constructor and spreads to the sub-argument the application of the same map. You have to generate projections for every argument of every constructor, and to show at some point that this composition cancels out, but not, in this case, you can see how this could be difficult, and this is not something that you would like to do by yourself, and this is why we're trying to do it automatically. And the strategy about avoiding the elimination of equalities is done in this way. So for generating the left-hand side, I do induction on both cases of the inductive type, and since I have an hypothesis, it's meaningful on the diagonal because you can discriminate outside it. On the right-hand side, you do induction on the binary parametricity relation, which also instantiates the inductive types on the diagonal, which then in the coherence property get to compute if you do induction on the relation, and you get a term that gets generated in the middle that you can prove that you can cancel as well. And you can do this regularly for the inductive type class that I described. And just to give you a hint of how this looks like for Liszt, I'm avoiding the boilerplate. This is just the terms that you have. This is just the type of the terms that you need to give to Trocq, and I'm able to generate that terms with those types automatically as well. So that's all I have. I'd be happy to take questions.
Questions?
There's something I did not understand in the talk, because you showed, in the beginning you showed two types that are the same semantics. But then when you talked about NR and list R, you were relating two types that were the same. So where's the gain?
So exactly. So this. So there's no automatic way of generating the relation between two types like arbitrarily, but because how it's done in Trocq, the user currently has to give these relations for relating the type to itself, for being able not to translate the goal from, so for instance, if you have a type that you don't want to touch in a goal, appearing in a goal, you need to provide this kind of relations. And this is, for the case of NAT, of course, relates the type with itself. But for the case of lists, it's relating, so given that you have a relation on the type parameter, you have related lists on the related type. Yeah.
Hey, so I'm just curious, like, is it a time issue or is it an issue with indices? Because you say you don't cover it yet.
So yeah, I haven't addressed it yet.
Other question? Okay, so let's find our speaker again. And